reservoirs to the viaduct deck, underneath the bridge launcher. To ensure sufficient storage space, the areas designated for storing vissoirs were expanded at the dike. The transport of the vissoirs from the prefabrication site to the installation site occurred every night, with 2 to 3 vissoirs being transported daily. In parallel, marine operations took. One of the critical aspects of the electrification work was the installation of overhead line equipment in key sections of the route. The Chipping-Sodbury Tunnel, Patchway Tunnel, and the Severn Tunnel all underwent substantial upgrades to accommodate the new electrified system. Additionally, supporting masts were strategically placed along the open track between the tunnels to ensure a smooth and uninterrupted power supply for the trains. Over the past couple of years, the electrification work on the Bristol to Cardiff line has been a significant undertaking as part of the Greater West Programme in Wales. The aim of this ambitious project was to modernize the rail infrastructure and improve the efficiency and sustainability of train services in the region. To accommodate the required clearance for the electrified trains, several bridges along the line had to be replaced. In Magor, 3 bridges Rogiat, Llandavenny, and Huggets were entirely rebuilt, ensuring that they could accommodate the increased height needed for the electrification project. Further down the line, Bridge Street in Newport and Splot Road in Cardiff also saw the replacement of their respective bridges to meet the necessary clearance requirements. Newport Station, a crucial hub along the route, underwent a complete overhaul during this electrification work. The station was modernized and upgraded to accommodate the electrified train services efficiently. The improvements at Newport Station not only benefited the travelers, but also contributed to enhancing the overall passenger experience. Furthermore, a specific area called the Patchway Gap received attention during the electrification project. Devegetation efforts were undertaken in this region to ensure the safe and reliable operation of the newly electrified rail line. By clearing vegetation along the track, potential hazards were minimized and the risk of damage to the overhead line equipment was reduced, ensuring the longevity of the electrification system. The Viaduct du Littoral, also known as the Coastal Viaduct, is a significant infrastructure project being constructed in Reunion Island, intended to become the main structure of the future Nouvelle Route du Littoral. As of the beginning of 2017, the construction progress has seen several notable milestones. One of the key components of the viaduct is the deck, which has now been connected to its land support, known as the abutment. To assemble the deck's different sections, called vissoirs, a specialized bridge launcher measuring 278 meters in length and 28 meters in height has been deployed at the installation site. Each standard section of the viaduct, known as a flao, comprises 28 vissoirs. The bridge launcher efficiently places 2 vissoirs every day, facilitating a steady and systematic construction process. During the month of February 2017, crucial earthworks were carried out at the D2 dike in Grande Chaloupe. These earthworks were crucial in allowing transport vehicles to directly deliver the vissoirs to the viaduct deck, underneath the bridge launcher. To ensure sufficient storage space, the areas designated for storing vissoirs were expanded at the dike. The transport of the vissoirs from the prefabrication site to the installation site occurred every night, with 2 to 3 vissoirs being transported daily. In parallel, marine operations took place with the involvement of the barge Zorite. This barge was responsible for installing the first 4 piers of the viaduct, spanning from P48 to P45, with the installation of the 5th pier, P4, underway at the time. Prior to each pier installation, marine earthworks were conducted using SDI floats and a Pinocchio hydraulic excavator, amounting to nearly 500,000 cubic meters of excavations for the entire structure. Following the installation of each pier, backfilling was carried out around them to ensure their stability, especially during cyclonic swells. Additionally, a Vibro flotation soil improvement campaign was initiated in late 2016 and was still ongoing to enhance the stability of the foundation. At the 2 prefabrication sites located in La Porte, production activities were significantly ramped up. At that point, 10 piers had been completed, and more than 20% of the prefabricated vissoirs, amounting to over 300 units, were ready. The factories were operating at full capacity, manufacturing 3 vissoirs per day, with a total of 1,386 vissoirs needed for the entire viaduct. Constructing a complete pier, consisting of 2 sections, took approximately 20 days. The weight of these elements varied depending on their location within the viaduct. A standard vissoir weighed around 300 tons, a vissoir on a pier weighed 700 tons, and a pier base, the lower part of the pier, weighed a substantial 4,000 tons. The construction progress of the Viaduct du Littoral in 2017 showcased the impressive scale and complexity of the project, with critical elements, such as the deck and piers, steadily taking shape. The viaduct's completion was gradually becoming a reality. The dedication and efficiency of the construction teams, along with the utilization of advanced machinery and techniques, were instrumental in ensuring the successful realization of this vital infrastructure project for Reunion Island. The North Channel Bridge Replacement Project in Cornwall, Ontario, Canada, marked a significant milestone in modern engineering. The endeavor aimed to construct a cutting-edge, 1,100 feet, 335-meter highway bridge with 4 spans over the majestic St. Lawrence Seaway, connecting communities and facilitating smoother transportation in the region. The construction commenced with the fabrication of the steel bridge superstructure, a remarkable feat accomplished using 22 box girders. These girders were meticulously designed and constructed to withstand the immense weight and stress of supporting the highway bridge. The project's engineering team tackled the challenge of varied girder lengths, with the longest girder measuring 108 feet, 33 meters, and the heaviest girder weighing a whopping 95 tons. To efficiently install the bridge, a state-of-the-art method called the launched girder erection technique was employed. This involved the use of counterweights and a lightweight girder section, known as the steel launching nose, mounted at the front of the structure. This ingenious approach allowed for minimal structural loads during the launching process, ensuring the safety and stability of the bridge. The counterweights played a crucial role in controlling the rolling moment during the bridge installation. By placing them at the rear of the assembled structure, the construction team could accurately guide the bridge towards its designated position. This meticulous alignment was essential for ensuring that once the operation was completed, the extremities of the box girders were perfectly centered on their respective supports. The entire launching process was carried out with precision and care. As the construction team worked to maintain the balance of the bridge, they gradually withdrew the counterweights once there was equal weight distribution at the rear and front of the main bearing. This withdrawal marked the commencement of the assembly's slow roll on the nose girders, a moment that required utmost focus and expertise. Throughout the launching process, a specially designed roller system provided support to the immense weight of the bridge beams. This roller system played a vital role in the safe and efficient installation of the bridge superstructure. It allowed for controlled movement and ensured that the bridge components were carefully guided into place, guaranteeing that the weight distribution remained consistent and balanced. As the project progressed, 12 PF series fixed pot bearings were installed at piers 1, 2, and 3, further enhancing the bridge's stability. Additionally, 8 PMG series unidirectional pot bearings were integrated into the abutments, providing essential support and flexibility to accommodate various forces acting on the bridge. The successful construction of the North Channel Bridge was a testament to the prowess of modern engineering techniques. The use of launched girder erection, along with the strategic placement of counterweights and advanced bearing systems, demonstrated the dedication and expertise of the project's engineers and construction teams.